Good morning, everyone. We'll solve this numerical on SFD and BMD of a simply supported beam. Is it recording? Okay. Now, usually they give the numerical along with the diagram like this. You're supposed to draw shear force and bending moment diagram, and the problem is given with either simply supported beam or a cantilever. Now you see a simply supported beam. Now you understand in the simply supported beam there is one fixed hinge and there is a movable hinge, and therefore you just need to find out the reaction forces at the two ends. If there are no forces acting horizontally, there are just two forces acting vertically, so it's called a simply supported. You know that. Now let me actually name these points. Usually people name this as ABCD. I'll use the same convention from left side. Okay, I use this here, A, B, C, D, and at this point A, the support, what it does is it actually produces a reaction force, and I call this as RA. RA stands for reaction at A. Reaction means whenever there is a support, suppose if I apply a load, there is a reaction from the support. So therefore this is called as RA, which is not known to me. This is again called as RD, which is not known to me. I need to find this two, and finding this two will give you 2 marks. Okay, and at B there is a force acting downwards, which is of 6 kilonewton. 6 kilonewton. Here there is a force acting which is of 3 kilonewtons, and each of these are actually placed at 2 meters. So there is no UDL. There are 2 point loads here, and there are 2 supports here, and we need to draw SFD and BMD here. So usually when you draw this diagram in the examination, you reserve the place below for drawing SFD BMD, and I've seen many people try to do the calculations here and draw SFD in some place, BMD in some place. It should not be that. Now it should be SFD and BMD should relate to this point, and it should be below. So you can reserve this place for SFD, you can reserve the place for BMD, and do the calculations somewhere else. Okay. Now let us find out RA and RD, and for that we already said we do use 2 formulas. One is moment at A is equal to 0. The sum of the moments at A is equal to 0, which means that at this point, if you actually take the beam, the clockwise moments which actually make the beam to rotate clockwise, and these anti-clockwise moments which make this beam to rotate, their sum is 0, because the beam is not moving, the beam is not rotating. Since the beam is not rotating, I say the moments acting on that are 0. So okay, so with respect to that, so I take the moments about A. Now this force cannot be taken RA because it is about A itself. Okay, the distance is 0, and here you got 6 kilonewton at 2 meter distance. So I take it as plus because it is clockwise. 6 kilonewton into 2 meter distance, and again there is one more full force here, which is actually 3 kilonewton acting at 4 meter distance. That is also clockwise. So anything which is actually going like this, you can take it as clockwise. Anything going with the ulta direction, it is left to you. So if you are taking one as positive, you should take the other as negative. So then you got 3 kilonewton into 4 meters, and there is only one force which is actually going anti-clockwise on the other end, that is the reaction force. So that is minus RD into 6 meter distance. The sum of this equal to 0. So here when you calculate this, 6 kilonewton meter into 2, so this is actually equal to 12 kilonewton meter, plus this is 3 into 4, this is again 12 kilonewton meter. This is equal to RD into 4, so RD into 6 meters. So RD you can say it as, so 12 plus 12, 24 kilonewton meter divided by 6 meters. So meter cancels out. It is left with a value of how much? 4 kilonewtons. So 4 kilonewtons. RD value you got it as 4 kilonewtons. I think by common sense, if somebody makes a mistake, okay, he doesn't have to actually serves the answer somewhere else. So you can see here, since the loads on the left side are more, obviously RA will be more. Okay, so here suppose if this was instead of 6 kilonewton, okay, instead of 6 kilonewton, if this value was 3 kilonewton, so can you guess the value of RA? Instead of 6, if this value was 3 kilonewton, then can you guess the value of RA? Here you got 3, here you got 3. It is symmetrical. So how much should be the value of RA? Come on, man. Huh? 3. So 3 kilonewton. Obviously, even without calculation, you could have said, since it is symmetrical, you would have a load of 3 kilonewton. Imagine that somebody is carrying a load like this. It is something, and there are two loads. The front person carrying a load here, the rear person carrying a load here. And suppose if these loads were equal and at equidistant from these two people carrying on the shoulders, definitely they will have the same load. So 3 plus 3 is 6, and divide by 2, definitely 3. So it is not symmetrical, it is slightly offset onto the left side. So that means that there is more load onto the left side, which means that you will see that right side load is just 4 kilonewton. 6 plus 3, total load is 9 kilonewton. Out of that, only 4 comes to the right side. Remaining should go to how much? Remaining will go to the left side. So sum of the moments equal to 0. You have found out this. You don't have to do all these calculations. So you can just write this directly in the calculator. You can calculate this and actually put this answer. You don't have to do this. I only did this to show you. Okay. Then you say that sum of the forces. Sigma stands for sum, and F forces equal to 0. So there are forces acting downwards, there are forces acting upwards. So forces acting upwards are RA plus RD, and forces acting downwards. Forces acting upwards should be equal to forces acting downwards. So 6 kilonewton plus 4 kilonewton. So 3 kilonewton. So 3 kilonewton. So what is the value of RD? So RD is already known to you, that is 4. So 6 plus 3, 9. 9 kilonewton minus 4 kilonewton. So equal to 5 kilonewton. So you understand that this value is 5 kilonewton. So up to this, you should not take more than 1 minute to calculate this. Okay. So once you have found out this, you have actually set a platform to continue the problem. If you go wrong in the first step, you will lose marks in all the other steps also. So sometimes you can also have a check by actually trying to do a small check, not with others sitting on the next, sitting beside. You can check yourself by trying to do instead of MA, you can do it on, I'll erase this again. Instead of MA, you can take it as MD. Sigma moment at D is equal to 0. Now should get the same answer. If you're taking moment at 0, then these moments are anti-clockwise, this moment is clockwise. So if you're taking moment at D is equal to 0, this is only a check. What I'm doing is a check. Okay. So sigma MD is equal to 0. So these moments are anti-clockwise. So from this point, 3 kilonewton minus 3 kilonewton into 2 meters, and again minus 6 kilonewton into 4 meters, and this 5 kilonewton into how much? 6 meters is equal to 0. Sorry, now this 5 kilonewton is known to me already, but suppose if you don't know this, you have to replace as a RA. Okay, so now you are finding out RA. So RA again comes to be how much? 5. So if you are checking this, so here these two, so 3 into 2, 6, and here this is 24. So 6 plus 24, 30. 30 divided by 6, it is 5. So you got the answer as 5 kilonewton, which is the same as this. So that means you have checked the answer from the other side also. So you don't have to lose marks, you have checked. So this is only for check, you can write this. Please write these steps up to this point. Okay, I think you can write this later once the problem is complete, because I'm recording the video. Okay, so right now what I wrote here, this is only for check. You don't have to do this every time. If you're not sure, then you can do this. It's only for check. Okay, once you have done this, then you can start doing drawing this SFD BMD, shear force and bending moment diagram. So first we'll draw shear force diagram. So shear force diagram, what I am drawing is not a beam, it is a zero reference line at these 3 points. Okay, now I said last time, if this is the beam, suppose if this is the beam, if this is the section that you considered, these are the sections that you consider at various points in the beam, because you want to draw, it's almost like a graph. It's almost like a graph for the value of SFD at various points in the beam. Now at various points in the beam, I take section here like this. And for that, the rule that we usually follow is, suppose if the shear forces on the right side, suppose if it is going down, it is positive. On the left side, if it is going up, it is positive. This is the convention for the positive shear force. So it is what we follow. Okay, so please follow this shear convention, the shear force convention. So now using this convention for shear force diagram, I'm now doing this. Now I'm continuing this. Imagine this beam to be continuing like this. No issues, you can continue. Now, we said last time, the shear force at any point is the sum of the forces either onto left side or right side. Now I take this section here. Now there are a lot of forces onto the left side, don't calculate. See if there are any forces onto the right side. Are there any forces? No forces. So shear force at this point is 0. Again, if you come to this point, again there are no forces, it is 0. Again at this point, there are no forces onto the right side, it is 0. But when you come exactly onto this point, even then there are no forces onto the right side. But when you only come to this point here, okay, you see, now if you come to this point here, the section just onto the left side of this point D, when you come to the left side of the point D, exactly almost at no distance, you see a force going upwards. What is the value? 4 kilonewton. But as per the convention, it says going downwards on the right hand side is positive, but it's going upwards. So up to this point it was 0. Up to this point it was 0 kilonewton. But suddenly when you cross this D, it becomes -4. -4 means, now people may ask me, so now what should be the height? You draw some value here. Usually it will be like, the values are like 4, 3 and 6. So usually take a small distance, it's of some convenience. Now to subconvenience, it's left to you. You can take 4 here like this. 4 need not be 4 centimeters or something. You can take it as like maybe like 4 centimeters or like 2 centimeters or something, proportionately, but you don't have to measure exactly. If you're taking 4, 6 should be slightly more than that. 8 should be double of this, something like that. Okay, you don't have to exactly measure this, but the pattern should be proper. Okay, now so I had actually 0 shear force here, and when I came here, then from 0 it became to 4. Again when I'm here, now what is the force on the right hand side? Now what is the shear force on the right hand side? That's 4 itself. Here also it has 4 going upwards, here also it is 4 going upwards, here also it is 4 going upwards. So at all the points here it will be 4 only. At all the points it will be 4. And until it crosses one more point here. So until this point, up to this point it is 4. And here it crosses one more force here. Now there are 2 forces on the right hand side. Okay. Now if it is downwards, it is positive. So is it downwards here? Is it downwards on the right hand side? Yes, it is +3. And this is -4. How much is +3 and -4? -1. It goes from -4 to -1. -1. You don't have to write it as -1. You don't have to write it as -1 here. Because anything below 0, it is minus, obviously. You don't have to write it minus. Okay? So it is 3 this is 1 kilonewton. It becomes 1 kilonewton here. And now, as you continue this section here, it is now +3 -4, +3 -4, it is -1 only. And I'm not writing -1 as you said, because it is below the 0 line. If it is +1, it will be above 0 line. Now again cross one more force here. Okay. Now can you tell me, now this force going down, is it positive? It's positive, +6. This force +3, how much? +9. This force -4. So 9 minus 4, how much? 5. So Now it should go to 5. So 4 was this much. 5 should be slightly bigger than that. 5 should be slightly bigger than that. So it should go here. So I've drawn here. And again, when I have sections onto the right hand side here, okay, again I say 6 plus 6 plus 3 minus 4 and all the points. And some people don't want to see on the right hand side, then they suddenly start checking on the left hand side because it is easy for them. You know that if anything on the left hand side is upwards, it is positive. If you see here, if you see this side, going upwards is positive. How much? 5. So now you don't have to calculate on the right hand side. Some people will shift from right side to left side now as per their convenience. So because we said shear force either onto right side is equal, it is equal to whatever you calculate on the left hand side. So they will shift from right side to left side. It will remain as 5 until this point. And again at this point you will see that suddenly there is 5. So 6 plus 3, 9 minus 4. So it is plus 5. Again there is one more force. What is this force? Is it actually upwards or downwards? It is upwards. Upwards is negative. So it is plus 5 minus 5, it becomes 0. So shear force will start at 0 and end at 0 here. Okay. So here, now after drawing this diagram, usually what you are supposed to do is, you are supposed to hash this area with lines like this, because the sheets that you use are actually ruled sheets. So it will confuse where you have drawn the lines. Those lines which you have drawn may be matching with the lines and it may not be clear. So these lines will actually make it clear for the examiner that these are lines above and below the 0 line. Okay. So usually you get around 40% of the marks for drawing SFD. And as engineers, what they do, they will see in which section you got the maximum shear force. At this section, you got maximum shear force. It was -1, here it is plus 50 kilonewton. Here it is 40, like this. So 50 to 50 kilonewton here. Okay? Sorry, it's not 50. How much it is? 5, sorry. 5 kilonewton. 4 kilonewton, 1 kilonewton. So which means that, suppose if somebody is predicting this is going to fail, it has got maximum chances of failure by shear at this point. It has got the least chance of failure between what points? Between what points? Least chance of failure between B and C. As engineers, you can see it has got least chances of failure between B and C due to shear force, because the value of shear force is very, very less. Don't worry whether it is positive or negative. What we are interested is whether it is, only the value, not whether it's positive or negative. So once you have drawn this, once you have found out this, you get around 20% of the marks. For this, you get around 40% of the marks, remaining 40% of the marks for bending moment diagram. So bending moment diagram, guys, so people use calculations, but I did not actually show calculations how to do this, because it is just addition and subtraction, so I did not do this. Maybe I need some space for calculation for this BMD, but I don't need this space for this. So this is one more diagram. The previous diagram was called as SFD, shear force diagram. This diagram is called as BMD, which is bending moment diagram. Moment means it is actually force into distance. So here, if this is the beam, suppose if this is the beam, if there is a force acting upwards, which makes the beam to sag like this, it is positive. And again for a beam, if you apply a force like this, it again sags, it is also positive. So now the forces acting upwards, both on right side and left side, are positive, which creates sagging. Okay, so it is the convention for bending moment diagram. So I have written the convention right side so that you don't confuse while calculation. It is the convention for shear force, it is the convention for a bending moment diagram. Okay, at any section, if the forces are upwards, it is positive. If the forces are downwards, it is negative. But what you need to do is, you need to multiply this distance with the force. Here that distance did not matter. Here the distance did not matter. We simply added -4 plus 3 plus 6 like this. Now this 2 whether it's 4 meter distance, 2 meter distance, that did not matter because shear force was only adding or subtracting forces. Here we need to consider force into distance here. Now we start drawing the bending moment diagram. For bending moment diagram, I again start with the right hand side here. Okay, right hand side here. Now for this beam, if I consider a section here, bending moment is force into distance. Now are there any forces here on the right hand side? No forces, no bending moment. Basically now to say that suppose if there was a scale here like this, suppose if it was a regular scale, I mean maybe it's not visible in the video. Suppose if there is a steel scale which is used to measure length placed here, and I actually place this steel scale on two supports like this. Apply a load here. Then you'll see that the steel scale would actually try to bend like this. Now, one thing you have to see that from here to here you'll have a curvature like this. But do you feel that this portion is straight or curved? Guys, this portion, is it straight or curved? It is straight. So that means only whenever there is bending, the shape starts to change. So suppose if this beam is continued like this portion of the beam would be straight because it is not from here to here. You can see here, this is A, this is B, this is C, and this is D. Okay, so this portion will be straight, and even suppose if you extend like this, okay, so don't worry about this diagram. I'm only trying to give this, so don't use this ABCD, it will confuse you. From this to this point it will be straight, which means that wherever the beam is straight, that means there is no bending moment. Even in this case, if you consider the beam here, when you load like this part of the beam would actually sag, and this part will actually have a shape like this finally. Will have a shape something like this. But this part of the beam will be straight because there are no forces bending it. Okay. So there is no bending forces here, bending moment here. So it will remain straight, and up to this point you can see here basically. So very similar to shear force diagram, bending moment at any point or at any section is sum of the bending moments either onto right side or left side. Sum means what? You should actually use this convention. If it is going upwards, that force into distance has to be taken as positive. If it is going downwards, that force into distance has to be taken as negative. So here, if I consider here, if I consider there are no forces, no distance, so it is 0. It is 0. It starts with 0 here. Now, as I actually move across this point, there is one force. What is the force, man? 4 kilonewton. What is the distance? Very, very small distance. 4 kilonewton into almost 0. It is 0. So that means with no distance, bending moment is still 0. Force is in kilonewton, distance is in meters, so I am writing 0 kilonewton meter. Okay, because moment is actually force into distance. Again, I now start shifting here, and this is 2 meters, no? Imagine that I am at a distance of 1 meter. Then what will be the value? Force into distance, what will be the value? 4 kilonewton into 1 meter. It will be 4 kilonewton meter. Okay? Is this positive or negative? It's positive because it is going upwards, and as per this, it will try to sag the beam, and it is positive. And it will go from 0 to 4 initially, and again, if I am here, then it will be how much? How much? Come on, man, what is that? It will be 4 into how much? 4 into 2, 8. So definitely 4 will remain constant, but it is increasing with the distance here. As the distance increases, the value of bending moment increases. So therefore, it will keep increasing like this from 4 to 8. It becomes like this. So earlier, so it is a straight line here. It's a straight line. Don't draw curved lines here. It's a straight linear relationship here. It will go from 0 kilonewton meter to 4 kilonewton meter positive. Okay. Now, the same thing can be done. I mean, here again you can actually do this. When you again cross this point, now how many forces here? 3 kilonewton into 0 distance, no distance. But this 4 kilonewton into 2 meter distance, which is actually 4. As I move this here, it will actually decrease or increase. So let us see. Let us move to the other point. So usually what people do is, for bending moment diagram, they write this calculation. Bending moment at D equal to 0. Bending moment at C is, it is 4 kilonewton meter into 2 meter distance. It is plus 8 kilonewton meter. Guys, here it should be 8, no? Here it is 4, here it is 8. Here it is 8. And then here, as I move here, let us not worry about any point here. Let us move to the next point here, up to this point. When I am here, there are two forces on the right side. So, one force, bending moment at D. Bending moment at D is 3 kilonewton meter. Guys, this is 3 kilonewton meter, positive or negative? It is negative. It is minus 3 kilonewton meter into what distance? Into 2 meters. Plus, this is 4 kilonewton, 4 kilonewton into what distance? What is the distance here? 4. What is the answer now? What is the answer? Minus 6. Minus 6 and plus 16. So that is plus 10 or minus 10? Plus 10 kilonewton meter. So it goes from a plus 8 kilonewton meter to plus 10 kilonewton meter. So now approximately, if this is 8, definitely 10 cannot be less than this. It should be slightly more than this. So I write here 10 kilonewton meter. So 10 kilonewton meter. And again, whenever there is no UDL, whenever there are only point loads, this relationship, the change in the value will be only linear like this. Okay. Now if you wanted, you could have actually checked this. If you felt this was lengthier, you could have checked this shifting to the other side. Instead of seeing on the right hand side, you could have seen on the left hand side. So at point D, instead of seeing on the right hand side, what is this point? This is not D, this is B. This is P. At B here, you could have seen 5 kilonewton meter into what distance? 2 meters. As per the convention, anything going on cup side, left side or right side is positive. So 5 kilonewton into 2, you would have got the same answer. Same answer you could have got easily. So 5 kilonewton plus 5 kilonewton meter, plus 5 kilonewton into 2 meters, that is plus 10 kilonewton meter. You could have got it. So you can shift from right to left the way you want. Okay. It is only a counter check. So you can counter check on other sides. Suppose if you want to actually ensure that you are getting full marks here without actually making mistake, you can check on both the sides and confirm the answer. It is 10. And then if I actually am here, guys, if I am here, what will be the value? It will be 0. Instead of seeing on the right hand side, see on the left hand side here. So A is 5 kilonewton. What is the distance? Almost 0 distance. So very close to this. At A, bending moment at A will be equal to 5 kilonewton meter into 0. 5 kilonewton meter into 0 meter, that is 0 kilonewton meter. Again it becomes 0 here. It goes to 0 here. Okay, so here you are actually understanding the variation here, and in the examination, once you have drawn this, it is always better you try to shade this area by hatching lines, because it will actually ensure that the answer is clear. Okay, what does the engineers do with this diagram? They understand that suppose if this beam is loaded, like this, beam is loaded like this, there is very less chance of failure at the supports, failure due to bending at the supports, because at supports bending moment is 0. Guys, this is engineering, please understand. If you are trying to break a stick holding in your hand, if you are using a knee, where the stick will break? Will the stick break at your hands? It will break at your knee. Where the load is maximum, there the bending moment will be maximum. Suppose if actually two people are actually using the knee, one is using 6 kilonewton, other is using 3 kilonewton here, and the beam is of 6 meters length, then there is highest chance of failure at what point? At B, because B has the highest bending moment. Okay, this is how engineers decide where they should ensure extra welds, maybe extra metal to be added so that it doesn't fail there. Otherwise, it will not fail here. There is less chance of failure, there is more chance of failure. Wherever there is more chance of failure, to prevent failure, you may add some extra attachments, or you can make the material larger here so that the failure is reduced. Something like this. It is the reason why we are drawing shear force and bending moment diagram, not for engineering students to do some calculation and forget it. Okay, it is the purpose, but we are trying to learn this. It is how you try to do this. So once you have completed this diagram, so usually most of the examiners won't check this calculation. Suppose if the diagram is right, and suppose if the diagram is wrong, they may actually check whether you have tried to do it with some sense. Okay, so usually if the diagram is right, so that means RA and RD values are right, and if these values of SFD and BMD are right, they are not going to check these calculations. So please ensure that the diagram is right. But if the diagram is not right, then they may see these calculations. Then it may help you to show the calculations and show that you have tried to do something but you have still gone wrong, and maybe some marks should be given. Suppose if you are right, full marks for this. Nobody says this. Okay, so this is how SFD BMD is drawn. So 20% of the marks goes like this for here, 40% of the marks goes for this, 40% of the marks goes for this. Okay, so similar problems would be given.